So we'll get rolling. Cool, hi. What do you guys do?
I don't even know myself.
Yeah, me neither, that's all good. Maybe we'll be simpler then, maybe. What program are you all folks in?
Honors physiology?
Physiology?
Yes, also physiology.
Physiology, awesome.
I'm in immunology.
Immunology, cool. My mom used to teach, well, Mom used to lecture in your course back in the year, didn't she? Yeah, cool. Computing science, awesome.
Biosci.
Biosci? Biosci as well. Okay, cool. So we have one computing science. So I was trying to decide what to do today. That doesn't mean you don't do like computing science and various other things. It's just what program you're actually enrolled in and what kind of requirements. Is it a master's or a PhD program? Undergrad. Okay, awesome. So then I don't have to ask you who your supervisor is, and then make sure that I don't say anything inappropriate for various supervisors. Cool. Okay, so I have various things I was planning to do today, and one of the things I think, I don't know. Remember maybe the first lecture I gave in this course for Kim was on sort of the foundations of machine intelligence. And I know you've had Rich talk to you, you've had Osmar, right? They probably told you some things. My view might be a little different, so I figured, hey, why don't we actually go back to that first talk I gave, which really was, hey, what can machines learn? How might they learn that thing? And when might they learn it? And I've even got some nice little activity sheets that. Yeah, I got some activity sheets you can do in pairs at the end as well as sort of a last exercise to have you running around the hallways and actually starting to get inside the mind of a digital learner. So we're going to be a bit more hands-on today, if that's all right with everyone. Otherwise, I can sort of try to switch onto a slide deck and feed you slides, but I'd rather not. Okay, so first question then is okay, we're an hour and 20 minutes? Mm-hmm. Okay, awesome. I love the room. This room makes me so much happier. This is a great room. It's cozier. Anyway, what did Rich and Osmar, and did you get Randy as well this time, or just Rich and Osmar?
Just Rich and Osmar.
What did they teach you? What do you know now that you didn't know before?
Well, Osmar told us a lot about the history of AI and the development from its inception all the way up until sort of the developments in rivaling human intelligence in the various fields and
cool.
what those steps were up until now.
Cool. And the AI winters and all that stuff. And yeah, I thought so. I think I saw the slides. Cool. All right. What else? What else did you go over?
I think there was an overwhelming focus on the cultural aspects of AI and integration in society and the risk it poses through both speakers. So.
Anyone else? No?
We also talked about the different ways AI learns, so
oh, good.
different ways of creating the cloud that you put an input and then it gets an output.
Mm-hmm.
Different ways of making that.
What are those ways?
So one of them.
We're going to do it again today, or at least my view on it. We'll do my view on it today. So.
Also single and binary, in which you provide various sets of data, and it will either categorize it as individual parts, or it will have two distinct dichotomous ways. So, for example, yes or no, black or white.
And then another way was having a neural network, so that it you have to put a lot of inputs for it to have an accurate output.
Right, deep thinking, was it?
Yeah, deep learning.
Deep learning, that's all trendy. People love deep learning. It's oh, hey, I have this widget. What's going to make it more trendy or more ready to get venture capital? Oh, it has to be deep. We'll make it deep. We'll make it a deep learning toaster. It'll be so much more marketable as a deep learning toaster. Cynicism. Okay, so any other thoughts then on what's intelligence?
AI or?
No, well, I mean, sure, but that's a little too narrow, maybe. What's this intelligence thing? If we're all talking about artificial intelligence or synthetic intelligence, what's intelligence? That was obviously helpful if we're trying to, tack extra modifiers onto it.
Ability to learn and ability to adapt.
Cool. Okay, yeah, ability to learn and adapt. I'm going to jump back over here and we'll just scribble some stuff on the board. Pink looks good. Adapt. Learn. Cool. What else?
Being able to apply your knowledge in different scenarios.
Ooh, okay. Knowledge. Let's do knowledge first. You said knowledge. That's good. And then different scenarios. Good.
Problem solving.
Problem solving.
Fall under knowledge or creativity, which also
Oh, geez. Oh, that's a tricky one. Let's do it in green over here. Creativity. And you did problem solving as well, right?
Yeah.
What do you mean by problem solving?
Problem solving, being able to use separate pieces of knowledge and your intuition to be able to derive to a proper solution.
Cool. Cool. Okay, other thoughts? What kind of stuff might go into intelligence? That thing we hopefully all have. I think we agree we have it.
Wisdom.
Wisdom. Oh, ho, define that one for me. That's like someone spitting out consciousness. All right, so maybe we can dodge that one for today's discussion. We'll find out whether we can or not. Whoa, I may even fall off my chair. So wisdom, what do you mean?
Wisdom. Okay, so this Webster Dictionary obviously has something.
Sure, it does. Yeah, dictionaries are great for that.
Yeah, but I don't have anything of the sort. I could just define wisdom as just the ability to be able to use ethics, be able to use, your own intuition of right and wrong, and being able to come up to I can't elaborate more than that.
That's fine. Anybody else? Thoughts on? I mean, you can chip on thoughts on wisdom as well.
Might be like applying like your own experiences and learning from them.
Okay, so learning from, not just learning, but learning from
Your own personal experiences.
Okay, and now is that different then from learning from someone else's experiences?
I would agree. I think it's debatable. You can say yes and no. If you're learning from other people's experiences, you're only learning the consequence of said action. Whereas if you're learning from yourself, you can say there's specific set of actions that led you to do the action. Right. For example, there's an emotion that drives you to do the action.
Ooh, that's a tricky one too. We'll put it over here.
Oh boy.
Okay, cool. Yep, that's fine. But that's there's internal states or signals or drives that we might think about, and emotion might be one of them. That's good. Cool.
I guess we could define it, or?
Oh no, there's only so many. Like if this is a candidacy exam, maybe, but no, we're gonna hold off on that. But that's okay. So that's really good as well. Actually, I do have. Oh, I could have brought the other worksheet too. There's one that's like learning from your own. We're actually going to do an exercise at the end. Well, again, I said you're going to send you out in pairs, and you'll learn from your own experience. But there's also a worksheet from learning from other experiences. We call it off-policy learning. But that's so we'll look at that one. Okay, cool. Anything else that you think like we missed anything here? Is it all good? We're missing all sorts of things. That's okay. Maybe I'm just going to grab another one of my Technicolor just to match the wonderful ball that Dr. Sola has provided us with. I'll use another color. What do machines do right now? Of the things we have on the board, I've got some other stuff I'll put in the board in a second. But what are machines already good at, or what can machines even just do?
Learn, problem solve.
Learn, sure. Problem solve, sure.
Have knowledge.
Okay, yeah. And this is one of my graduate students is working on exactly defining that. You remember Alex Carney, took the class in previous years. A lot of her stuff is starting to center on what it means to know stuff. So I think that if we brought Alex here, we'd have there'd be hot debate right now. There'd be people arguing about things. We could say that depending on how you define knowledge. Yep. How do you define knowledge?
I would say maybe on a machine level, just having the definition for a term or just knowing how to do something.
Okay. Oh, okay. Cool. So definitions, and also I'm going to call it policies, because that's what we typically talk about in the computing sciences as a way of acting. So you might have knowledge, which is, and this is great because it's getting towards what the actual. I'm going to try and remember all the slides I've given in previous lectures and do them all free form without looking at them. It's going to be awesome. But you might remember definitions or assignments or the way that a pattern of stimulus begins to connect to some kind of other pattern of stimulus, be it a term or a name or a forecasted outcome, or a simpler way of collapsing that same concept into something even more precise, or it might be ways of acting. This is really good. What else can machines do right now of the things here?
They can adapt?
They can't, yeah. You suggest that one, I think, too, right? I think you did. Yeah, they can adapt. That's really good. I mean, you have smartphone, like 10 probably smartphone. If you use a series of apps in a certain location, like I'll pull mine out and be like, you suggested app, Pokemon Go, or your email. Like, our machines do adapt in very, very subtle ways. So that's like, you could very, very convincingly argue that case. Anything else on here? Do we think that they, like, so knowledge of different scenarios as well is another one that I think is actually very, like, you could imagine that as an understanding of state or future next states. There's a whole literature in the brain and also in the computing sciences on successor representations, which is knowledge of different future scenarios, if maybe is a coarse way of saying it. What about creativity and emotion? Those?
Yeah,
Yeah?
probably to some extent.
Yeah? How so?
Well, so they can make you, I mean, machines can make you feel various emotions. So
Okay, yeah, that's the thing I believe.
they're, transacting with them, whether they can feel it themselves or something else, but, their, ability to make us happy and sad and stuff, hopeful.
Is your eyeball?
Yeah.
Is your eyeball still working? Do you have your?
Yes.
Okay, good. Are you toying with the idea of flirting with another new model eyeball that was just released, or are you going to stick with your tried and tested robotic canine companion?
They don't exist here yet, right?
It's hard to get.
The ones that are like, you speak to them and they change your house lighting or something, right? So they're kind of combining Aibo and Alexa. Yeah.
For better or worse. Okay, so I'm going to put a question here, and I'm going to put a question here. What about wisdom and ethics and stuff? Did you have the ethics talk yet? Did you have your? Yeah? That's how, okay, good. That's why you're giving such good talk about ethics. So yeah, question marks, X's, check marks. No, okay, sure. I'm okay with that. They're not wise. We do not have wise machines, maybe. Cool. All right, that's all good. So I like this. That was a good starting point. So maybe the next thing to talk about then is the learning bit. So could a system that does not learn exhibit intelligence? No, why? Please.
Because it'll just be static. Like, there's no going forward from that point.
Yeah, so I mean, I'm inclined, given my line of work as well, I'm a reinforcement learning researcher, I'm inclined to agree with you. But let's imagine, let's just to sort of confuse things a bit, let's imagine that you had a gigantic lookup table. You had this gigantic, essentially dictionary, like maybe the Chinese room, for those who are familiar with that kind of example. But imagine you have IBM Watson or something like that has the answer to every question you might know. It actually knows all the things that might be known. It's functionally omniscient. It never changes, but it knows everything. Would that be intelligent? Like, I mean, people might argue it would. That's why I'm pressing on this one, is that people might argue if you had a system that knew all the facts that there were to know, and if you asked it a question, it would give you the answer, told you how to do something, it told you the answer. They might say that like people would colloquially say that I was intelligent.
Wouldn't that be the same for a calculator then? Because you need an input in order to get an output.
Yeah. Yeah, so you could imagine, like, is a calculator intelligent?
Yeah.
Yeah, you say yes.
I think if you can't learn, you can still be intelligent.
Okay, so that's, I think a lot of people might agree with you as well. So I'm not actually going to say whether I do or don't. I like the view that systems have to continue to learn, because to learn is to adapt. And I think those two things are very, like, you could imagine adapting in a fixed way, or having some kind of recipe book that tells you how to adapt to the world. And then maybe that's not learning. Maybe you're not changing yourself based on what you see, but you're changing your way of operating in a fixed way in response to the world around you. Maybe that's okay. But I think let's at least make sure that we tease apart the idea that there might be systems that learn, and we might call those systems intelligent. There might be systems that do not learn, and people might call those systems intelligence as well. So as long as we can tease apart those two things, then we can start to think clearly about both. A system that does not learn, the expert systems of days of yore. You'd have someone very clever would go in and start programming a series of rules into a machine, and the machine would run out in the world and enact those rules. You can imagine a really simple one, which is like I make a Lego Mindstorms robot. I put a little downward-facing sensor, I put a black line on the ground, and I make the black line curve around in a little racetrack, and I write a piece of code that says, hey, if you go off the line, turn left and get back on the line. If you go off the line this way, turn right and get back on the line. The thing follows the line. Heck, you could even write a little fancier piece of code that would take it to its charging station or take it to the light or take it to dark areas of the room. Maybe some of you have made robots like that just for funsies. You could show that to certain people and they'd say, yeah, that's intelligent. Is it learning? No. Is it adapting? Not even really in a very substantive sense. It's adapting to its immediate sensory stimulus. But people might still call that intelligent. So as we debate what is intelligence and what is synthetic intelligence and how should society interact with intelligences in general that we might have created, we should be very, very watchful of the idea that people might call a toaster intelligent, they might call a phone intelligent, and they might call something that is smarter than a human being intelligent, and they might talk about it in different ways. Is that okay? That is like actually okay though? Is that reasonable? Do you think that that's a reasonable thing to be like, okay, I agree that people might think about intelligence in different ways? No one's like, no, it's going to be one way. You can say that. It's okay. I don't have an agenda in this respect. Okay, great. So if we imagine that then, maybe it's really productive to talk about what's good about maybe a system that learns. I like learning systems, so I'm actually going to, and I know Osmar almost certainly told you about machine learning, so we're going to dive in a little ways there, I think. What makes learning beneficial? We do have systems that learn. We have intelligent systems that learn, and because of machine learning, intelligent systems, especially machine learning as being widely deployed in industry, or even the really advanced research versions of machine learning that maybe you won't see in your applications for a few years. Why are people caring about this learning thing? Like, why learning over just a really good expert design system or a hand-engineered system or a system that's like this gigantic library of Babel with all the facts in the world? Why is learning good? I got 3 things in mind. I'm trying to remember all my slides from your previous courses. All right, phones, get out of the way. So why learning?
I think the most obvious one would be efficiency, and that's really important in industry, so you can push your research that much further. But I think another not so apparent thing is something on the premise of security. So as deep learning becomes something more prevalent in society in the future, more people will have access to this technology. So I guess in a sense you have to figure out a way to protect your own stuff by using this technology. So
cool.
I guess in terms of function, it helps to have a machine that can learn and reduce its level of, related to efficiency, reduce its level of mistakes in terms of as of right now, what the function of that machine is, having the ability for it to reduce over time.
Cool. Which if you think about where we're seeing learning machines being applied, it's in the energy sector, the transport sector, the medical sector, the fintech sector. Like, essentially, you're seeing learning machines being deployed in a widespread way throughout all of the things how many of you have probably Siri or Google Assistant on your phones? Probably a lot, because they all come with it now, and they all use learned systems. That's a natural thing. So I think you're right. And if everything is using it, efficiency is going to be very critical. Any other thoughts about why learning is really good? I have 3 big points I'll mention in a second. But
you could also say that the world is constantly changing. Since it's not a stagnant thing, you can never have too much intelligence or too much information within a system. So,
bang, change is important. So that is, I think, one of the really critical reasons for learning, and actually a lot of the other things that you've talked about all come down to the idea of change. Is that so? Here's sort of the three ways that I like to break it down. I really like to break down the idea of why learning is good into cases where you might know where you are and where you want to get to, and you might not know how to get between those two things. Like, you might not know how to solve a problem. You may know what your starting conditions. You may know the endpoint you wish to get to, but the ways of getting from the start to the end are unclear. A learning system is a system actually has the capacity to connect the dots, to fill in the missing insight that might allow you to get somewhere from somewhere else. And this could be solving how to solve a problem. Think of a context, think of seating plan organization. I have a lecture theater, and I want all people with dark hair to sit not next to someone with light colored hair. But if someone has a purple sweater, then they can't sit next to someone with a blue sweater unless there's someone with a red sweater. Imagine these complex optimization problems. You might know what you want, but you might not know how to get that result. A learning system is able to start to automatically get those results, knowing what you want. Another thing is that maybe you actually know where you start and where you end, but if you were to try to actually implement that, it would be very hard to implement. It's a problem of scale. Maybe the complexity of the problem is such that you might know how to implement a very simple way of solving your problem, but because of the scale or the complexity, you just can't do it. There are certain problems that you could, I talked about that little line following robot. You could hand engineer a control policy for a robot to follow a line or to follow walls. As the environment gets more and more complex, you might actually be able to continue to engineer the system such that it's able to do what you want it to do, but eventually you're going to be pouring hundreds, thousands, or millions of engineering hours into creating the system. A learning system might be able to automatically scale up for you. And I think the key last bit, so this is really the things are unknown, things are maybe too complex, and the last one is that things change, and you hit on this one really nicely, is that often you know where you start, you know where you might want to get to, but that place might be going. The world might be changing under a system. If a system was truly omniscient, could see the position of all the molecules and all the atoms and all the electrons, all the fields, all the dark matter, maybe then the system actually would never have to worry about change. But we don't have systems that have that kind of eyes and mind. We have systems that are limited in their view into the world, like your view into the world. What's happening in the classroom next door? Oh, right? We don't know, but it might impact our world. And so we have to be able to adapt to things that we don't know, and we have to be able to change. That's a fundamental aspect of intelligence, actually, and I think it's a fundamental aspect especially of why intelligent systems that involve learning have capacities that we find desirable. Is that cool? Any questions on that? That breakdown? Those are the three for me that I think are really important. Questions? Does that make sense? Okay. If that makes sense, my big goals are my learning objectives. If we want to specify them as learning objectives for today, I'm not going to write them on the board because I'll just scribble them like the rest. My big objectives really are to have you actually begin to think clearly about intelligence and how people might talk about intelligence. That's a big goal for today. Another goal is to then think about learning and why intelligent systems that learn might have some kinds of benefits that we find desirable for our industry, for our society, for improving our quality of life. And then the last three bits, and I'm making sure that I'm staying on time so we have time for the exercise. I really want to get through what a machine might learn. And I'm going to break it down into three things, or essentially three fundamental pillars of intelligence that I usually think about. We'll talk about how a machine might learn, and relate it back to those three things, and then when a machine might learn. Okay, so that's my learning objectives for the end, and in service of those sort of last two chunks, I'm gonna we have an activity for you to do that will hopefully be fun and entertaining and also enlightening. Okay, so what might machine learn? And I would like to say that a machine or other intelligent system might wish to learn to predict the future, learn how to behave, and might learn how to represent the world. So I call it representation, prediction, and control. You see this regularly in the fields of machine learning. You see this in the names of the conferences that we often send our papers to as academics. Representation, prediction, and control are three things that you might wish to have a machine learn. Very briefly summarizing those, representation is how the information in the world might be structured. For instance, the information in this room, there's lots of ways that we might take all of the light that's reflecting off all the objects and start to think about those in terms of things like tables and chairs and people and instructors and cameras and markers and throwing markers at cameras. No, that's a policy. That's a way of representation, how information in the world is structured. We might wish for a machine to learn how to structure the information in the world. Does anyone have a really good, I'm putting you all on the spot because this is maybe not obvious right now. What's a really good example of representation, of a machine that's trying to find out how to structure the information in the world? We use it all the time. Does anyone have a good example?
Representation?
Yeah. Think of it as turning the complexity of the world into something that's more crisp, or to finding structure in the information that flows through the world. Machines do it regularly. Your phones probably do it.
Would a Roomba vacuum be one, or is that a stretch of representation?
How do you?
It learns. Well, you run it through the space, or you. I don't know the details of how a Roomba works, but eventually it learns a map of the floor of the space and obstacles that it will come to, and it will work around that to
maybe
vacuum your floor automatically.
Cool. So that actually, you might actually be involving all of the three things I said a machine might learn. But let's just look at the representational aspect of it. You might have a raw set of sensors that are coming in on the Roomba. Like, it depends on the model. I have a really old Roomba that didn't learn squat really. It had a random policy and bounced around. But the newer robots, of course, you could imagine that they have some raw sensors. They might be distance sensors that bounce off the wall. They might be downward facing sensors that could find out if there's a stair there. There might even be like dustbin sensors that tell you when dirt is coming in. There are actually, even the older Roombas. So if a system were to take those raw sensors and be able to try to figure out a more compact or compressed view of the world that said like table, chair, and use that to move about, you could very well think of that as a representational act. Deep learning actually is a very interesting way that people have found ways to take like broad, complex streams of data and turn them into representations that are actually more learnable for other tasks. So that's a good example. Another example is, maybe I'll draw this one on the board, see what happens. I'm going to write. Okay. Okay. I want you to write this exact same thing with only four numbers. You can pick ones and zeros or symbols, doesn't matter, but you get only 4 characters. How can I change those 12 characters into 4 characters?
They all have to be distinct characters? Before? No.
There's some information in that string of ones and zeros there. And I'm going to say, I need you to convey to me the same amount of information using only 4 characters. Give me a new string to write that has the exact same amount of information as that string. Looking at the computing science undergrad. Camera? Maybe the camera knows really well. The camera knows this. The camera's great at this.
Code?
So it's actually, it's something that happens all the time, and this is compression. So it's funny. We often think about representation in a very high level sense, but all of our devices, when they take a picture, they don't store the exact pixels of the image. They find ways to compress it, to simplify while retaining the structure, lossy and lossless compression. So here you might just say, oh hey, there's 3 ones in a row, and now 3 zeros and 3 ones. Oh, I have 3 ones and 3 ones and 3 ones. Right? Sorry, I need 5 characters. I'm sorry, my exercise is broken. I'm sorry. If you didn't get it because I had too many ones, it's my apologies. Yeah, sorry, that's my fault. If you had it and then you're like, oh crap, those extra 3 ones really threw me for a loop, then that was my bad for drawing. I got overzealous with my ones. But does that make, like, my glitch aside, does that make sense? That the idea you could start to see repeated patterns in the data, like, hey, symbols come in blocks of 3. So I don't need to actually keep all 3 around. I can just toss out 2 of them and just keep one to represent all of it. You could call this equally like A, B, A. That's fine too. Either way, you're starting to find ways to represent the data by finding regularities or structure in the data according to some measures. Now I feel really bad I drew extra ones, because you probably were all like, oh, I totally get this. And you're like, no, I don't get it at all. This doesn't work for me. 4, I can't do 4. Could you actually do 4? Maybe. I think you probably, anyway. You might be able to, but you might have to have another rule in place. Anyway, so that's an idea of representation, though. You're finding a way to represent the data stream in a simpler form. We may wish to have machines that learn how to do that, right? Like you may have a very complex, you do have let's say you have a robot, Kim's robot dog, faced with the squishiness of the wild world, and only has a couple of megabytes of EEPROM to store information, you might wish to find ways to simplify the world, to represent the information in the world that in a more compact form. So let's think of that as representation. Okay, is that okay? So the next thing I might ask then is that another thing we might wish. Let me just do this slightly differently, and this time I'm going to try not to break my example. I can't promise anything. Again, I'm flying. See my pants here, and let's do 0, 0, 0. What comes next? Yeah, that's a reasonable answer, right? Why is that a reasonable answer?
Because it's a pattern indicating both A, B, A, then you put B, so it will be the simplest that A will be next.
Totally. And let's call that prediction. You're predicting some kind of something about the world. It's a forecast. In this case, if imagine that this is actually the axis or the arrow of time moving forward here. Imagine that's your arrow of time, and you're seeing one symbol at a time. If I were to draw them one symbol at a time, and we were to be here, already, if I draw this symbol, what's the next symbol going to be? Sure. And probably the next one's going to be 1. Now what's the next symbol going to be? 0. Exactly. Cool. If we haven't set up a pattern, let's just say we haven't set up a pattern yet. Maybe it's something like this. You might say that it's 1. You might not have enough data to make a good assumption. You might say it's like 0.5. Who knows, right? If I were to do what's the next symbol? I can't tell. I just made those up. So exactly, this is a perfectly reasonable thing to say, that we don't actually have a good idea of what the next symbol in the stream is going to be. But one thing you might want to do though is you could keep some kind of statistics about the history, right? Like if we really don't know and we're like, one very naive thing we might wish to do is have the system simply keep around some kind of like an average, right? You could say like, okay, let's just keep a running average of what the symbol is, and then when we get to this new point here, it's like, what's this new spot? Well, if you have really good statistics on the world, you might guess, like here, are there more 1s or 0s? I didn't even count. Maybe there's more 0s? Let's pretend if there's more 0s, you might guess slightly below 0.5. So you might actually guess a 0 because you think it's more likely that a 0 will appear next. And you're trying to figure out what's going to happen. You could call that a prediction, but there's all sorts of complex predictions that we might make about not just the next symbol, but we might predict a whole next sequence of symbols. We might predict the way, like I might actually wish to know like, well, what's the sum total of the next 10 symbols I'm going to see? We may wish to know things about the immediate future, about the far future, about some way of weighting the future. We may actually care maybe more about the more recent future than we do about the far future. There's many ways that a system might wish to forecast how the sequence of time will unfold. There's lots of prediction in the world. There's lots of prediction problems where you might, like, mail goes through a mail sorting system and it's like, oh, okay, I need to automatically identify the postal code so I can send it somewhere smart. The system might look at the thing and say, try to classify the different digits and letters in the postal code, and then it's making perhaps a prediction about what letter this, like my writing you can see is awesome, so I might do something like this. What number is that?
8.
Yeah, sure, 8. That's a total. If I was a mail sorting program, I would probably call that an 8. Oh, what's this? Right? It's unclear. Maybe you're like, okay, hey, I'm a mail sorting program, and I noticed that that this is sort of on a slant. And 7s are typically more slanty. So, okay, so you might call that a 7. I might be really hasty in my writing, as we know I am, and it might be a 1. But that's also a kind of prediction. But notice that this is a different kind of prediction. Here we're predicting future events in the flow of time. Here we're predicting some aspect of what the visual stream is actually in front of us. These are all reasonable things to assume. You might wish to predict the future outcomes. We might wish to predict what something is. Nice to classify or cluster things in the world, classification in particular. So we might wish to have a system that could learn to represent the world, to understand or develop the structure of the world. We might wish to build systems that can actually predict the future of the world. Imagine that now, like, who has stocks or bonds or something, or if you do, I'm sorry for the recent financial, it's my fault, it's not my fault, but the recent financial crashes, who knows? If you have, for instance, some kind of securities, or maybe you're squirreling away gold under your mattress, you might care about the value of that thing over time. Maybe you collect Magic the Gathering cards and you really want to sell the foil ones for more money. Who knows? You may wish to predict the future outcomes of the value of something. Money is a very natural thing we wish to sometimes forecast. A lot of people make their careers on doing just that. You may wish a system that would be able to predict which stock you want to buy in the future, or what sequence of buying stocks might be important. Is that everyone cool with that? Does that make sense? Like, the whole fintech industry is really big on this kind of thing. And what I just said last is important because it gets us from predicting the future to making decisions. I said control or being able to take actions is one of the last things that we might wish a machine to be able to actually do. And in this case, you may wish to say, hey, what stocks should I buy in the next 18 months so that my portfolio grows in size? It's a question about how to act. And we might wish to have systems that learn how to act. So is everyone okay with that? It's something we, like the Roomba, we go back to the Roomba example. Hey, where's the dirt? We might actually have a Roomba that's trying to learn where in the room you take off your shoes. That's a natural thing. It's like, should I turn left or should I turn right? Should I move forward? Should I waste batteries by turning on the vacuum, by turning on the beater bar? Those are all policy choices. They're choices about how to act in the world. And we very much might wish to have our systems learn how to act in the world. This is a very important thing. So again, representation, prediction, and control are three things. And if I was Rich Sutton, or maybe some of the very, very old philosophers or psychologists, I might also say that it's very important that the action, the representation, and the prediction all happen in service of a goal, in pursuit of some ends. So maybe there's two kinds of action that I'm going to, that let's just have a look at. Just for simplicity's sake, maybe have a look at two ways of acting. I'm going to draw you a very, very simple world. It's sort of like you might call it a Markov chain, but no one here probably cares about Markov chains, so we're not going to call it that. We're just going to say, hey, they're like, you could be in any one of these balls. Okay? Let's say we start here. Now we get to, we take the only action available to us and we hop over to this ball here. We're now here. We have a choice. Oh my goodness, a fork in the path. Dunk. What was I drawing? There we go. Fork in the path. So the question then is, do you wish to go up or down? How might you make that decision?
Do you know anything about the two?
If you, what kinds of things would you wish to know to make a decision?
Talking about real world, right?
Sure. Or a fake world.
Trajectory or something like that?
Why would you go there versus there?
Just interest, I guess.
Oh, okay, cool. So one of them might have some like it might be more appealing to you in some way. Okay. Is that right? Yeah. Is that a way to say it? Okay, and that's absolutely right. So you might assume that I'm going to move your. Can I move your little tower, folks? Is that okay? Yeah. Awesome. Okay, so you might actually try to make decisions based on some kind of valuation or some kind of appeal. And it might be novelty. Like, this is a totally reasonable thing that, like, you might be like, wow, this is like, I don't know, full of dancing cheetahs and hyenas and a giraffe doing a headstand. And this might be like my lecture right now. Like, sure, you're going to go watch the head spinning, like, breakdancing giraffe, because this is probably not as exciting as a giraffe. Let's be honest. But let's even be more like, it may be a really boring kind of example, going back to the financial technology examples I was using, is maybe we actually know something about these and there's some value assigned to them. Doesn't matter how we value things, but let's pretend that we're talking about dollars, and maybe we know that like this is $500 and this is like, I don't know, 100 yen. Maybe I need an extra tick. Someone tell me if I drew yen wrong. Which one would you go to? Top. Yeah, top. That's like $1. Cool. Actually, probably less than $1. I don't know, more than $1 these days, slightly more than $1. right? So if you like money, which people tend to do, there's whole like, society set up around this sort of structure. Maybe it's 5 Bitcoins, I don't know, whatever. You would probably go that direction, right? Okay, cool. So what's important about this? You might be making a choice about how to act based on where you expect to be in the future. If there were 5 possible future options, maybe that's still tractable. How would you go about, so one question, how would you go about making those kind of decisions if the number of possible futures was infinite? Right, you'd have to find some way to slice this all up. If you try to do exactly what it has said, I say, hey, I gave you 10,000 possible future options from where right now. You could take, there's 10,000 possible actions you could take or future situations you could reasonably get yourself into. You'd have to keep around a list of the valuations and all of those things. You'd have to then be able to, in reasonable amount of time as a system situated in a world, begin to make a decision about which one of those you might go to. That's a very hard problem. So let's just, I agree there's some principal ways you might wish to start to truncate that space or to carve out that space or shape that space. What we just talked about is very hard to scale. So another thing you might do is you might make a decision based simply on where you are. Like right now you're in a classroom. Maybe you don't have to know what would happen if you leave the classroom. Maybe you just know that like my lecture is so boring that our videographer actually leaves the room. Like maybe that's actually a thing that you know just by being in the classroom. So in addition to making a decision based on the future states you might reach, the future outcomes you might observe, you might also wish to take actions based on just where you are. Right? This is a reasonable thing. And that might be where you are in space or where you are in time. These are all reasonable things to think, but you might wish to take actions like the Roomba, for instance. Maybe the Roomba doesn't have to keep a big map of the room and decide where there's dirt and where there isn't dirt. It may just have to realize that if I'm near a wall, I should always turn. The simpler Roombas did that kind of thing. They're like, oh, hey, my immediate situation, I'm going to react to my immediate situation. We may wish to have systems that learn both of these things. How to react to an immediate situation, how to learn, essentially we call this policy learning. The ability to learn how to behave in response to stimulus. We may also wish for systems to learn the values of future actions or future states, such that they could choose among those different options or future states. Those are both reasonable things that we might wish a system to learn. Is everyone okay with this? This is like the meat of what I wanted to, especially what I wanted to get through before we actually try out some of this. So representation, prediction, and control. And this is the 2 sort of views on control that I'm going to present to you today. This is obviously there's many things you might imagine. You can learn parameters, whatever. Learning parameters might be considered the latter case. We have the ability of systems to learn from data. This is something that in a technological sense is not surprising. In a biological sense is also not surprising. You may consider that some of the core activities of the brain are actually doing many of the things we just talked about. They're learning how to structure, the brain is learning how to structure the world. My wife has taken the level 1 sommelier course, and she's really good at telling you like where that white wine came from or what kind of soil might have generated that red wine. She's learned how to structure the different taste sensations in the world into a concrete representation that she can use to make decisions. So when she walks into the wine store, we get really good wine on the dinner table. It's fantastic. And so that's interesting because there's 3 things that happen in that little example I just gave you. My wife's brain has probably adapted, we call it perceptual learning, to be able to detect different nuances in terms of both smell and taste. She might use those representations in her brain to predict what wines on the shelf might be good. And then she uses those predictions and that representation to take actions such that she'll actually buy the bottle of wine, we'll take it home and we'll drink it. And it's going to be much better than the bottle of wine that I might have picked. Does that make sense? It's like the fusing together of representation, prediction, and control in pursuit of a goal. And the goal in this case might be having an enjoyable dinner with a wine that pairs really well with our food. That's my corny example that I just made up on the spot, but I think it actually does manage to pull together representation and prediction and control, and the idea that you might start to learn those things, right? You might learn by going into the wine store and actually trying the different wines, which ones you like and which ones pair better with food. Okay, quick time check. Great. So let's try to aim for another 10 more minutes of how machines might learn. And this is just sort of a very simple run through. And then is activities okay? Do you folks want to go out and do an activity? It's a lot more fun listening to you talk, I promise. Yeah? Okay, awesome. Okay, how might machines learn? I'm going to again break it down into three different examples. One of them is a really simple one. What color is this? Purple. Cool. What color is this? Sure, that's good. Seafoam, blue, turquoise. What color is this? Cool. What color is this? Okay, cool. If I were to tell you, I think it's indigo.
Oh, right.
No, I'm not saying it is. It doesn't even have a list. Don't worry. But if I were to tell you this is indigo, okay? What color is this? Indigo. Cool. And like, what color is this? No, it's salmon. I'm going to call it salmon. What color is this? Cool. That's learning through That's learning through labeled examples. And another way of thinking about this is the whole field of there's a whole field of supervised learning. You may hear it called supervised learning, but the key idea, and Rich Sutton also really argues that it's the idea of learning through labeled examples. Is that I show you a picture and I say that picture is Grumpy Cat. Next time you surf the internet and I show you that picture, I expect you to say that's Grumpy Cat, right? You're essentially saying you're pairing some kind of data stream with a label, or a result that you wish to have. It's a supervised learning process whereby samples and labels are paired together. Okay, so that's a kind of learning that again is called supervised learning, but often is called learning through labeled examples. Does that make sense? So the same thing here. Over time, you've all been exposed to the labels for this data stream. I say color and I point at this thing, and we've all come to agree that this is sort of brownish. Right? This is a label that we've learned through, like when we were kids, it's not like there was some innate, like maybe there was innate structuring of a visual cortex. Turns out there is, hooray! Like the whole back of our brain is settling and shifting even before we're born into a very complex set of patterns that can detect lines and edges and things like that in motion. But at some point, somewhere along the line, this visual pattern was matched by our language to brown. And we can imagine our machines doing the exact same thing. A machine might learn to make, the example is also those handwritten digits. You might present like 10,000 examples of crappily drawn sevens to a machine, and every time say, that's a 7, that's a 7, that's a 7. And if the structure of that machine was sufficiently complex, support vector machine, a deep neural network, it would be able to, when you show it another crappily drawn 7, it would be able to output the label 7. And then you could make a mail sorting system and everyone would be happy. Or you could make any other things that deep learning is being used to make, or supervised learning in the sense of support vector machines or LDA classifiers. I work in bionic body parts. The same thing happens with signals of muscle activity in the human arm from someone with an amputation. We make a single set of patterns and we map it to like closing the robot's hand. That's learning from labeled examples. Another way of learning might actually be learning from the inherent structure of the world. This is actually how we might learn representations. We might have some kind of measure of the world, like I want differences. So how might make one grouping in the, I'm going to make one grouping for you in the room. I might cluster the individuals in this room into sleeping instructors and not sleeping instructors. So this is like, if you're looking at inherent structure in the data, you might pull things out. There's all sorts of other things. I might say people with glasses versus not people with glasses. If I'm looking at dividing the people in this room into 2 groups or 3 groups, I may actually have a machine that learns to separate out. Imagine I give you a table full of marbles, and there's big marbles and small marbles, and there's red, yellow, and blue marbles, and I say sort them into 2 piles. You might make many different choices, but in a sort of an I just say I need 2 piles. This is like this is like a clustering algorithm. I say, hey, take all those marbles, divide them into 2 piles. You might divide them by big and small. You might divide them by colors that have red in them and colors that don't. There's all sorts of ways you might start to divide out the data in the world. There's an unsupervised or a way of learning the structure of the world based just on the statistics of the data in the world. That doesn't require any kind of observer to come in and say, this is Grumpy Cat, this is pink. Okay? Is that okay? That's sort of a more abstract example, but it's a way that machines might learn to separate out the data streams in the world based solely on some properties or statistics of that data stream. Is that okay? Yeah? Okay? Okay, great. Okay, last bit is the bit that I think we're going to spend the remainder of our time on. It's learning through trial and error. And I'm a reinforcement learning researcher, and another way of saying reinforcement learning is learning through trial and error. A machine might learn by trying things out and seeing the result. This is a really nice thing, especially if you have a problem where you might know, like, hey, having lots of dollar signs in the bank is good. How do I behave to do that? I don't know, but a machine might take actions. It might try out buying different stocks, and just go back to our stock example, such that it can try out buying different stocks, find out which ones are more profitable, and then do that so as to maximize that dollar signal. Maybe the signal is happiness. Maybe the signal is some other thing you want, like number of cubes of tofu that I have in my salad. Who knows? There's all these different things you might wish to maximize, and you may wish to try out different options so as to do that. The example, my wife going to buy wine at the wine store, it might be trial and error. She's like, hey, this one looks good. Oh, it's Sonoma region in California. Do I like those kind of wines? She'll learn by trying it out. Another example I use is an ice cream store example. Imagine you go into an ice cream store and there's like 10 bins of ice cream and they have like really wild colors and no labels. What do? You want to buy ice cream, just to be clear. Ice cream is good. Oh, you're smart. Yeah, totally. There's an exploration-exploitation trade-off that we have to think about, where you don't want to like commit whole hog to go and say, here's $300, I want that entire like 50-liter tub. No, you're right. You're going to be like, no, maybe I want a sample. You're going to try out a sample, and it might be really good. Okay, let's say it's, what kind of ice cream do you like? Oh, I was going to say, that's exactly the example I always use. I really like it too. That's exactly the example I was going to use. And like, okay, maybe it's mint chocolate. What do? Do you buy a whole cone of it? There's like 9 other ice cream. What do? You
get a sample of everyone.
So okay, that's a reasonable thing you could do, right? You like, maybe this one's really good, but you don't know about the other ones. So you're going to sample all those other ones, and then you're going to make a decision. If I say now there's 10,000 different bins, now suddenly you're sampling forever. You're going to be full before you ever get one. Maybe the rest of them are all like earwax. They're like Harry Potter Bots Beans style. There's like earwax ice cream and like, I don't know, like mushroom ice cream or whatever. Maybe that's actually good. I don't know. But you could imagine that like there's a sort of a trade-off when you're exploring the world. Sometimes you want to actually be maximizing your happiness, and sometimes you want to be trying out new things. This is learning through trial and error. The ice cream store example or the wine store example is a great example of learning through trial and error. And this is really the bread and butter of reinforcement learning. To do this really well, you might hope that the world is structured in such a way that you can see the differences in the world. If I send you into the ice cream store and you're blindfolded and no one can tell you what they are, you don't even know which bin you're facing, and I say get the best ice cream, you're going to be batting chance if you're lucky. Like you're just like, oh, that was awful. This mint chocolate, where was it? You won't be able to tell because the world is not structured in a way that lets you actually learn to make good decisions. So that's the idea that the interplay between representation, learning how to map that representation to expectations of the future, that's prediction, and then using that to actually take good actions. I'm going to buy that ice cream. I'm going to have a whole cone of it. And I'm going to be so happy. I'm going to fold into that mint chocolate chip, more chocolate chips, and it's going to be spectacular, right? So learning how to make good decisions. This is trial and error learning. The worksheet I'm going to have you folks do now. When machines might learn, I just want to touch on this very, very briefly. There's 2 sort of times when you might expect machines to learn. One is you might expect them to learn while they're receiving the data, right? The Roomba's bumping around the room. While it's bumping into the room, it's actually changing how it views the world. It's changing how it makes decisions. Another, that we call this the online, or I call it the real-time learning setting. It's when you're learning about the stream of interaction as it's happening. The other kind of learning might be that you see a large batch of data, and you take that whole batch of data and you sit there and you think about it really, really hard, and you change your internal structure, you change your learning mechanism based on that batch of data. So in supervised learning, the example I gave you earlier, like I have each one of you write like 100 examples of a really craftily drawn 8. I give all of those digits to a classifier, say learn this. The system is going to synthesize this giant batch of data, and in the end it'll have a good classifier. We call that offline or maybe batch learning. The other example is if you're immersed in a stream of time and you're learning about the experience as it's coming in, that we call that real time or online learning. And just to be clear, if you do ever write papers about online learning, you'll also get lots of notes from people who really care about e-learning and MOOCs and online education. Because apparently online learning is also online learning. So just be wary if you use the term online learning with people who are not in the machine learning community, they may think you mean e-education. I ran into that before. It's really rather complex. Okay, is that all right? So the thing you might learn from trial and error, and I'm going to actually give out your worksheets. You might learn about reward. You might learn about the goodness or badness of those ice creams. But you might also learn other kinds of things through trial and error. You might learn about any of the signals that surround you in the world or are inside your body as well. We have a paper on that recently. So here's your worksheets. We've got 20 minutes left, but let's actually do maybe work on these for 15 minutes. Divide into pairs, please. So work on them in pairs because it's much more fun that way. We'll go out, we'll come back at exactly 3:15 and spend 5 to 6 minutes debriefing. Is that all right? Here's your worksheets. I don't know if I've done this in your class before. Maybe I have.
Something like that.
I think I have. Okay, cool. So don't worry about the back page. You can keep it and do it later if you want. Okay, I'll hand out another set over here. I guess I've sort of divided you into partners without thinking. Cool. And what you're going to do, please just go out into the hallways here, find a corridor or a path or a hallway or something, and try to answer one or two of the questions that are on that front page, and do so just with the things available to you with your own human body. So don't take out tape measures, don't use stopwatches. It'll be important for when we talk about this. This is about learning from the stream of experience you are currently moving through. Jot down the answers to the questions and also how you went about getting the answers to these questions and how correct you think the answers are, or what you would need to do to make them actually correct. Okay? And so like just one example here is starting at one end of the hallway, how long is the hallway? How far is the other end of the hallway? Using just your body, how would you go about learning those values? These are really simple questions, but think of this, think of like you're a robot dropped into a world and all you have is the sensor, the values of the sensors coming into your little robot brain core. And you have to learn things like, hey, how far away are things? You have to begin to predict how far you could move before you smash into stuff. You might predict like the Roomba, I keep going back to your Roomba example, you might predict like how many wheel turns do you need until you see a dirty patch of floor. These questions are very much the real-time online kind of learning questions that learning systems all around us in the world face. So run out in the hallways in your pairs, try and answer these questions, do one or two of them, and be back around a quarter after, and we'll